Transformers. Robots in disguise. Okay, let's get started. Oh, that was so bad. Should I redo it? No, I can't be bothered. Let's be honest. Kid School has a demonstration transformer pictured alongside. Yep, right there. So it'll have coils, then a soft laminated core, usually made of iron, and we have copper wire around one, maybe less around the other. We plug something in, and we have some output. Right, we have a primary, so number of primary turns and number of secondary turns. We have a primary voltage and a secondary voltage. So the primary coil has 12,000 turns, so NP is 12,000, no problem. And it is connected to 240 volts RMS, right, to the primary. And she connects an AC voltmeter. Oh, that's AC power source. What's a voltmeter? You get a V, that's right, V for voltmeter. Connects it like so. And she measures the voltage across the 600 turn secondary coil. Great. And we're asked to calculate the value of this voltage. So immediately we see the number of turns has decreased, right? So we call it a step down transformer. The voltage will drop with the same ratio as the turns drop. So from that we can see 12,000 goes down to 600. So what's that divided by 200? So we know the voltage will be divided by 200. And from that we know that it's 12. However, if that's all a bit too much for you, you've got a formula sheet. And in the first column, fourth row, you're given NP over NS equals VP over VS. Right, this is the transformer equation, right? The ratio relating number of turns to the voltage across the primary and the secondary. So let's just write that out. NP over NS equals VP over VS. And we are calculating the voltage across the secondary coil. So we are solving for VS. So we'll multiply VS across, and we're left with VP. But then we multiply NS across and divide NP across. So NS over NP. There we go. And now we can just substitute in the values. So 240 volts across the primary, 600 turns across the secondary, 12,000 turns across the primary, which is 240 times 1 over 200. In other words, 240 divided by 200, which gives 12.0 volts RMS. And that is an achieved question. I do definitely recommend labeling the diagram with, where's my highlighter? Primary voltage, primary coils, secondary coils, and secondary voltage. Yep. Alright, and it makes sense. It's a step down transformer, so our final voltage is less than the initial voltage. Part B. The coils are held by a ring of laminated soft iron, which runs through the core of each coil. Explain why an AC voltage in the primary coil produces an AC voltage in the secondary coil. And we're told that they are wrapped around an iron ring. So, let's start with the basics. Alternating current, right? That means current is changing, right? It's alternating. It's it's got a sinusoidal shape, right? It goes between positive peaks and negative peaks and in between. So current is changing. What does that mean? It means the magnetic field is changing, right? Because there's a magnetic field, well, I should say magnetic field strength, technically, yep. A magnetic field is created around a current carrying conductor. In this case, it is the coil of wire. And so if the current magnitude is changing, the magnetic field strength is changing. What does that mean? This means that magnetic flux is changing. And so magnetic flux is a little bit different to field strength. So we can look at our formula sheet to recall. Phi, magnetic flux, does relate to the field strength, but also the area. In this case, the area is constant, but it's the field strength B that's changing, which results in the flux changing regardless. Okay, now we have a change in flux. And so with a change in flux, we look at Faraday's law. A change in flux over time causes an induced EMF. And so the secondary coil experiences an induced EMF as it sees the rate of change of flux. So voltage, or we could say EMF, is induced in the secondary coil, and just where that comes from is Faraday's law. Epsilon equals negative delta phi magnetic flux over delta T, the rate of change of magnetic flux. Okay, and are we done? Well, we've explained why an AC voltage is induced, yeah, but we haven't explained why the coils are there, or why the coils are wrapped around an iron core. So let's finish that off. Iron core or ring is needed to concentrate the magnetic flux. Is that enough? Guess we could say to maximize the induced voltage. And that would be good. So in summary, we have an alternating current in the primary coil. This alternating current causes a changing magnetic field strength, which means a changing magnetic flux. You can actually kind of just skip that line if you like. So the magnetic flux is changing so that there is an EMF induced in the secondary coil, right, because it experiences this change in flux, so by Faraday's law. And we have the iron ring to ensure the magnetic flux is concentrated through the secondary coil rather than sort of just lost out into the air, out into space. And that is an excellent question. Alright, moving on. Part C. Kate connects the 12,000 turn primary coil in a circuit with a 12 volt battery. Okay, and a 12 volt headlamp. Explain why the headlamp bulb only comes on after a slight delay. I don't particularly like this question because it doesn't explain this part very well. If you've played around with the transformer before and you connect it to a DC source, you'll note the lamp will turn on right after a slight delay, but then it will immediately turn off. And that's because the current is not changing, because it's a DC power supply. So magnetic flux is not changing, so the induced voltage only happens for that change near the start, right, when you turn it on. It doesn't constantly alternate. But that's not what it's asking us to explain. It's asking us to explain why, after you flick the switch, it takes a moment before the headlamp will turn on, and then it will quickly turn off, right? But it doesn't say that part. So 2 ways to explain this. We could explain it in terms of back EMF, or in terms of the time constant, right? Because a coil, right, transformer made up of coils are inductors, and when it's connected to a load, there's resistance, and so there's a time constant which limits the flow of current. But then, of course, the physics behind that is the back EMF argument. So let's go with the back EMF argument. So let's just bullet point it. So we close the switch, or I guess turn on or connect. Yeah, I'm going to say close the switch. In other words, turning on the 12-volt battery. So when we close the switch, there is a change in current. Right, it went from no current to, oh, hang on, there's a change in current now. And this change in current, if we look at our formula sheet, 4th row, 2nd column, this back EMF depends on a change in current over time, right, rate of change of current through an inductor. So close the switch, change in current, so back EMF created. I'll just state the equation. All right. And what does this back EMF do? Well, the back EMF limits the change in current. Right, it opposes it. It's in the opposite direction. Yeah. Is that it? I think that's it for excellence. Let me just double check. Excuse me, I mean for merit. Yep, so that would be a merit. And for the time constant argument, it is very similar. So we would say that in an LR circuit, which this is, right, the inductor being the transformer, resistance being the load, the time constant is L over R, which limits the rate of increase of current. Hence, there is a delay in us seeing the bulb turned on. All right, and question D. This one, a little bit unusual. Haven't seen this one pop up before. But, you know, we can solve it. It's honestly level 2 and even level 1 physics knowledge, but it is, yeah, the context is a little bit confusing. So let's try unpack that. All right, so the power station generates 50 kilowatts of power. So P for power. The transmission line near Kate's house carries 50 kilowatts, again, of power to an industrial user. The voltage across the transmission line is 220 kilovolts, so 220,000 volts, and the resistance of the line is 4 ohms for every kilometer. Calculate the power lost as heat energy across a distance of 300 kilometers. So actually it's the power lost, right? As opposed to just energy, because we're not given a time. Yeah. And then part 2, comment whether this amount is significant compared to if the voltage is not 220,000, but is only 25,000. Cool, so spoiler alert, the reason why we have high voltage power lines to transmit electricity is because it reduces the amount lost as heat. So I'm thinking in question 2, we'll find that if it was only 25 kilowatts, there's a lot more heat losses. But let's work towards that. So part 1, the power lost as heat energy. So that heat energy is lost through the resistance of the line. So we know we're going to need to include resistance. We know power as current times voltage. Yeah. However, you may have also seen power as current squared times resistance, or voltage squared over resistance. So that's just putting in Ohm's law. So if we put in IR in for V, we'd get I squared times R. If we put in V over R in for I, we'd get V squared over R. And so in this case, these power equations right there account for the resistance. So this will be the power lost as heat energy. Yeah. So to start, we'll want to work out the current traveling through the transmission line, then use the resistance of the transmission line and the calculated current to work out the power losses. The reason why we don't want to use this equation here, well, I mean we could, but there'd be an extra step, is that voltage is not the transmission line voltage, but it's the transmission line voltage for 300 kilometers, which we are not given. Right? Whereas we can calculate the current with the transmission line voltage and power. So, go back, go forward. Here we go. Let me just get rid of that and that. There we go. So, in part 1, we want to work out the current. So finding current through the transmission line. So current is equal to power over voltage, where power was, what was our power? 50,000 watts. And the voltage was 220,000 volts. Yep. And that gives us a current of 0.227 amps. Great. Now we can relate that to the power lost using our second power equation. So finding power losses. Power equals current squared times resistance. And now what is the resistance? Well, it's 4 ohms per kilometer for 300 kilometers, so 4 times 300, which gives 61.98 watts. So that is the power lost in 300 kilometers, which compared to the 50,000, right, the power output is very small. This is insignificant. compared to the 50,000 watts. Right, it's quite efficient. Now in part 2, we perform the same calculation, but instead of stepping it up to 220 kilovolts, right down here, it's only transmitted at 25,000 volts. So let's do the same. So I equals power, 50,000, divided by 25,000, which is a nice 2.0 amps. And then the power loss is current squared times resistance. And so what's that? 4 times 1200, 4800. 4800 watts. Now that's close to 10%, right, of the 50,000, which is significant. This is significant. Significant at almost 10% power loss. Whew. And that would be an excellence question. And what my answer isn't super clear at explaining is that in this part down here, the current is larger as the voltage is less. So just putting that into words, so just sort of an amend point there. As voltage goes down, current goes up for the same for the same resistance, and this causes the power loss to go up. Right, so just explaining that a little bit better. We did it with an equation, but it asks us to comment about it. Cool. All right, well, that's that question done, and cheerio.